So the first problem we'll be doing today is this problem of a stepped bar, where our objective is to find the nodal displacement and element stresses in the bar. Uh, Dimension wise, these are the cross sectional area, these are the length, and the modulus of elasticity is same throughout the bar. So directly we'll be moving on to the Abaqus. So this is our software UI. So we'll start with create model database with standard explicit model. And first of all, we'll do is set work directory. So like this will help us access the files easily. So I'll be changing it to D and FEA project and do OK and do OK. So now our file will save it in D directory and I'll name it as first problem. And since this is a statically indeterminate system, like one would have studied in solid mechanics, so I'll name it like that. First, we'll start with part. In part, we'll go with 2D planar and wire because it's a 2D object with a very small. No, our focus is 2D object, so we'll simply take this and the approximate size we'll do as 1000. It's something to do with the units. So yeah, so first we'll refer the problem. Okay, so first we'll need to make this 300 line, then this a different line. So I'll use a line 2. So click here and we'll use the coordinate system. So first we'll enter 0, 0 our starting point, and second point will be 300, 0. This is our one step. Then our last point will be 700, 0, and we'll enter. So we have created our line which depicts this step bar, not complete, but yeah, that is the starting point. Then we'll be making this straight support. Okay, this also we have to do. So, yeah, so again we'll take the part. Now since that is a rigid body, we'll go with discrete rigid and wire, and again continue. It's again a part 2. Okay, so again we'll make a line. So here the coordinates will be, we should remember what the previous, this was 0, 0, this was 700, 0. So this point we can assume as 100 in y and 703.5 in x. Okay, so we'll do that. 703.5 in x and 100 in y, and we'll click enter. And the opposing point, this point will be negative. Okay, so x remains same and y becomes negative 100, and press enter and just click on cross and click on done. So we have this straight line. After this, what we'll do is we'll add a reference point just at the center of this straight line. Okay, so this will be used in future. Then yeah, that's all for creating a part. And now we'll go to the property. So in this module, what we can do is we can assign properties of the material, like I'll show you. So in here we can go to mechanical elasticity. Here the general Young modulus Poisson ratio. So we'll rename this material as, let's say, steel, and we'll say Young modulus as, here it's given. So it's GP. Okay, so make sure the unit is mm. Okay, so when we convert GPA, it's 200 into GPA is 10 raised to 9, if I'm not wrong. Then it will become 10 raised to 3. So Poisson ratio is missing, so we'll 0.3. Okay, and that's it. We'll close it. And now for the section, we'll go for beam and we'll go for truss. Continue. Cross-sectional area as shown here is 250. Click OK. We have created section 1. Now you can see that here one section is already created. Now since we have two different cross-section areas, we'll create one more. This will be 400. Same material. Here we can change material, but here it's same. So we have two sections. After creating material and section, this is material, this is section, we'll have to assign that section to the part, right? So here the area is only on this section, right? Area is on only this part, this 700 mm, not on this vertical line. So we'll assign the section to this part. So to assign that, we'll have to go to this. You can hover and see assign section. Click on it. Click on the line where we want to assign. Click on done, and then it will give an option which one you want. We want section 1, which is 250 mm square, and just click OK. See, it has turned to green. It means section has been assigned. Now we'll go to second line and again click on done and assign section 2. So it shows type is truss, material steel, and okay, it has also turned to green. It means section has been assigned. Okay, before that, it just went out of my mind. We need to do something here. Yeah, partition. So why partition I'm going to do is, you'll observe that here it has been this 400 mm bar has been divided into two different, like it is two elements. So we'll partition it in the beginning itself. Okay, so using this, going to tools and using this partition, right? We'll use this edge, type is edge. We want to partition edge and we want to partition using midpoint because it's centered. So clicking on that, we'll click on this and select a point on the edge is saying here. So we'll click on the point and partition definition complete, create partition. Done. So now we have three parts here. So we'll close this and we'll observe. Okay. We can observe it later on when we have selection to make, that we'll have three parts here. So yeah, again the section is complete. We'll move on to next assembly. So in assembly, this is something that one should follow this step. So we'll assemble both the parts, part 1 and the part 2 that we made. Okay, and let it be dependent, mesh on part, and just click OK. This is a step that we must follow. Then again go to step, next module, go to step manager. This is a by default which is present, and we'll create our own step based on the loading we want to put. So this is static general problem, right? Yeah, like a static problem. Things are not changing with time, everything is stationary. So we'll go with static general and continue, and let the things be default here, or if you want we can put here 1 and 1. So what this option does is, instead of the loads we give, instead of applying it slowly like it was there before, it was incrementing it at certain sizes. Here it will put the load at once, like instant load. So we'll just do it, and yeah, that's it. That's the only step to be done here. Next, interaction. So this is something new that you might not observe frequently. So interaction between this bar and the static support that you have made, this rigid support. So we'll zoom onto it using this tool. So if we just make a square where we want to focus, it will zoom on it, right? So this is our area of interest right now. So we'll put this, then we'll go to interaction property manager. create. So the interaction we want here is contact between this bar and the vertical support. So we'll click contact and continue. Here it has to be a mechanical contact and a normal contact. Let the things be default and just click on OK where it's been created. Now go to this first option, create interaction, surface to surface, continue, and we click on this surface. Okay, just click on done. Now which choose the side for the edges. We'll click on yellow and thus choose the secondary type. So interaction from between this point and this point. So we'll click node region and this is our node. Done. Let the things be default here. Just click OK. So you will see there in the messages interaction into one has been created. Now we'll click on this auto fit view so that things come into the view. We are done here. Now we'll go to loading. Yeah, now we need to check on our question. So what kind of loading we need to do? So here the loading or boundary condition, one of the very important things that we need to observe in a question. Here at this point it's a fixed support, right? The fixed support and the loading here is on this node 3. I may 1 2 3 4. So this is third node, a loading of 70k Newton. Okay, so we do both together. So first we'll create this boundary condition of this symmetry, anti-symmetry, and caster. Like multiple options are here. So we'll just click on continue and click on this node. Done. And we'll do last option. Like it's a fixed support, so block every degrees of freedom. Okay, see now this that is a boundary condition. Now the loading is at 75 kilonewton at third point, right? So we'll click on load. It's a concentrated force, yeah, and we'll click on continue and choose this point. Then this value is 75,000. Okay, so this has been done. Next, meshing. So yeah, so this is something that generally comes, make independent this error. So if this occurs, we can go to part and this won't occur again. So yeah, first we have to create mesh. First we go to this option of seed edges and we select the entire area of interest and click on done. And we will go by number and we'll reduce to 1. Make sure you reduce it to 1 because we have already done the partitions before. If you increase it to 4, then what will happen is every partition, like we had 3 partitions, right? So every partition itself will get created into 4 parts. So we'll have 4 3 are 12 elements. But here if we do 1, things will remain same. Just click on 1, see, same, 3 elements. Now we need to choose the element type. So we'll go mesh, element type. It's saying select the region to be assigned. So we'll select this region, click on done, and in this family we'll select truss. We'll see this T2 D2 came. So this is what we want, a 2D linear node, 2D truss, and we'll click OK. So that is the element assigned to this geometry. That's it, and then we'll mesh part. It has not been meshed yet. We just created elements. We'll click mesh and we'll just say OK to mesh part, and you just click on yes. You'll see that 3 elements have been generated on part. Yeah, we are done. That's it here. Now the final step is job. So job is like creating the solution. So we'll start the solution. Create. You can name it anything you want. Name it solution. And you just click on continue. Here it will be a full analysis. Everything possible that it can find out about this problem, it will find. We'll see job solution has been created, and then we do data check just to be sure that part 2. Yes. So yeah, it will check data for any errors. When error. Yeah. So the issue that I was facing was the part 2 was not meshed. So yeah, part 2 does not require meshing, but I just meshed it with 10 elements, so that won't change the result in any way. After the data check is completed, you just submit the solution and you just submit. So data check is better in terms of like finding these kind of errors. It's like compiling your code before uploading it, right? Something like that. So yeah, job solution completed successfully, and we'll just see results now. So yeah, in results, we'll click on plot contour or deform shape. So this is the deform shape of your bar under a loading of 75,000 Newton and a fixed support. So first, my area of interest is this displacement, right? So instead of just looking at this random colors, we'll do a much more closer analysis. We'll go to tools and query. We'll click on node and click on pro values. So here we can click on individual elements, or we'll just probe nodes and get the magnitude of desired point. So at 1, you'll see, you just click on 1, you'll see data is saving here, and then hover over it till you get second node. Yeah, this is our node 2, this is our node 3, and this is our node 4. Yeah, so these are node values. Okay, so we'll compare it with our solution and see. uh, yeah, see, these are the solutions, right? So I'll highlight it. So u1 is 0, u1 is 0. At node 2, it's 0.45, that's matching. U3 is 0.6375 and U4 is 0.6375. So yeah, both are matching, right? Node ID and the magnitudes. Okay. So we'll just cancel it. We don't want to save it. No. Right. So that is one thing we have verified. Now, next thing is support reaction we want, right? So we'll click on RF and we'll see that support reaction is this value 7, 5 and 4 zeros, right? See, 7.5 and 4 zeros. So this is also matching entirely. Again, we can do this pro value and we can see the value at this node. See, it's 75,000. So that also matches exactly. Then what else we want is this von Mises stress, right? So these are the values: sigma 1, sigma 2, sigma 3. Okay. So yeah, again probe values, and this time we'll do element and see. Minimize this. See, now we are doing element, not the nodes. Okay. So I just selected in probing elements, not nodes over here. So see, element 1 300, element 2 187.5, element 3 0. Same as exactly as this: element 1 300, element 2 187.5, element 3 0. Now some of you might be thinking, like in the solution, if you compare that, the distance between this, like the elongation in the step bar is less than 3.5 mm, right? But why the bar is crossing the fixed support? This is because of a scaling factor. It's like an exaggerated deformation it's showing. So we'll go to the option, go to the common, and see the scaling factor is 110. So if it is 1 mm, it is showing 110 mm. We will go uniform and make it 1 and click on OK. So this is the actual deformation. Hardly any deformation. So just to get a closer look, see, it's not touching. So that gap was enough for the bar to expand. So yeah, that's it.